Dear participants, let's get forward with another session. In this session, we will be performing the experiment of number 2, section 1, IAVOC 105. This is based on the study of PN junction characteristics. A comprehensive manual is being provided to you in which you will be getting a brief theory of diode operation, the diode pin out, identification of diode terminals. Everything has been given in a very comprehensive manner. The static IV characteristics has been also given, and this is the characteristic that we have to study through this experiment. Now remember that whenever you are performing some experiment, you should be very clear about which components you are using and what are the equipments that you require, especially in this analog lab experiments. And whenever you are using some equipment, you might need some power supply, ammeters, voltmeters that are very common. Remember, in such cases, you need to mention the range. For example, we have written here that this is a regulated power supply which should be able to supply us 0 to 30 volt DC. We need a digital ammeter. That digital ammeter is a dual range meter. You can find 0 to 200 microampere or 20 milliampere. In both ranges they should give a reading, and in digital voltmeter you can see it is 0 to 2 volt and 20 volt DC digital voltmeter we have used. So we can very easily use a multimeter for our purpose, and that we will be using during the demonstration. Now you can easily see that we have the circuit diagram, and we are very familiar with the forward diode characteristic circuit. This is the same circuit what you can see here. There is 0 to 15 volt power supply. Then in series with the diode there is a 1 kilo ohm resistance, and in order to measure the diode current there is an ammeter. You can see this is 0 to 20 milliampere is the range, and as you can easily find that this ammeter is connected in series with the diode because we want to measure the circuit current or the current through the diode, therefore it is in series. Definitely all ammeters should be connected in series. Now you see we are also interested to know what is the voltage across the diode, and therefore this voltmeter is connected in parallel to the diode. Now this is the reverse bias circuit. You can see very easily that here the direction of the diode and here the direction of the diode, they have not changed. Okay, only the battery polarity has been changed. So now you can find anode of the diode is connected to the negative terminal of the battery, while cathode of the diode is connected to the positive terminal of the battery. So now we can see that the diode is simply reverse biased. You can also find that there is a series resistance that is connected with the diode. Now here the microammeter is there, and again we have connected a voltmeter across the diode to find the voltage that is developed across it. So this is the very basics of the circuit, and we have already gone through such circuit in our theory coursework. The procedure has been given here. So we need to connect the circuit, then we need to vary. In forward condition we need to vary the voltage that we apply across the diode in steps of 0.1 volt up to 5 volts, and we need to note down the corresponding readings of IF. Here VF is the voltage across the diode and IF is the current through the diode. Now once we have got these set of readings of voltages and currents, then we need to plot the graph. Similarly, we have to go for gradually changing the voltage across the diode in steps of 0.5 volt up to 8 volts. Okay, across the diode when it is in reverse bias condition, and we need to note down the reverse current also. We can also go for different that is reverse current that we need to plot over there. All right, now you see that this is our forward biased condition tabulation table or observation table. You need to put this observation table when you actually write your manual. Then on the ruled page you should write all these things on the white page you should put your observation tables, circuit diagram, etc. Now you see this is the diode in forward bias condition. You can find the voltage that is applied across the diode, and this is forward current through the diode. And similarly, you can also tabulate your results in this table in case of the reverse biased condition. Now see that we need to draw the graph. This is the characteristic and it is most important. You will find that the graph sheet you have to divide in 4 equal parts, because ultimately you want to draw this thing. This particular characteristic is expected. Okay. So you take the graph paper from the central part, you divide it equally into 4 coordinates. Fine. On the right axis you have forward voltage, on the right x-axis you have got the forward voltage, on the left x-axis you have got the reverse voltage. On the positive y-axis you have forward current, and on the negative y-axis you have got the reverse current. So in this way you have to distribute the coordinates. Now see that you have to plot the voltage that you are getting across the diode in x-axis, and you have to note the forward or reverse current in y-axis. Therefore, remember that in x-axis we always plot the independent variable, and in y-axis we plot the dependent variable. Here, whatever voltage we are applying across the diode, that voltage is developed, right? So that is an independent value, that is an independent parameter. Now when that voltage is applied, then some current is flowing through the diode. So that becomes a dependent variable. So forward current is a dependent variable that depends on the voltage that we apply across the diode. Okay, so this is the basic static IV characteristic, and with this much introduction I think that we should be able to perform the experiment. At this point I will be suggesting you one thing, that you should put in result some of your observations, like what is the cut-in voltage. Cut-in voltage we have studied the particular voltage at which the diode starts conducting in forward bias condition. Okay, so we have studied all these things. Now it is the time to see what we had studied, whether they actually happen or not, and we have to write down your conclusions. Whenever we are using any electronic component for certain experiment, we should be very careful towards the important specifications. Now you can see that here some of the important specifications of diode IN4007 that we will be using for this experiment has been given, and also at the end of this manual the data sheets for IN 4001 to 4007, the complete family specification is given. So you remember that it is actually 1N4001, but it's my habit to call it like IN4007. So it's 1N4001 to 1N4007. So the diode that we'll be using for this purpose is 1N4007. All right. So at this point, I would like to mention one another thing, that we will definitely perform the experiment. But I would like to show you another very important way of learning the thing. That is, you can, by sitting at your home, you can simply simulate the entire atmosphere. And for that, Indian government has taken a very beautiful initiative, and in that initiative, different prominent institutes of the country, including all IITs, they have helped us to develop the virtual labs. So if you use this virtual lab, then while sitting at the comfort of your home, you will be able to perform the practicals. So I will be showing you the simulation, and then we will actually perform the practical. Okay. So in order to go for this simulation, definitely you need an internet connection, and then you have to write like this: virtual lab. So you can see this virtual lab IIT Kharagpur is already there in my menu. That's why you can see this at IIT Kharagpur virtual lab. Okay, so you have to click it, and then at the very end you will find basic electronics lab. So you click over there, you find the list of experiments. Now you see there are 17 different experiments. Okay, so that you can perform. You literally do not need any component for this. However, your idea should be clear about what you are doing. And even if you commit a mistake, you are not going to destroy any equipment, and therefore you can be very confident while working. I will go for experiment number 5, VI characteristics of a diode. So you can see the theory has been given where we are going to explain the structure of a PN junction diode, explain the function of a PN junction diode, explain the forward and reverse bias condition of a silicon diode and a germanium diode. So comprehensive theory is given here so that you can have no confusion about the experiment that you are going to perform. The procedure has been written. You can go through them. And then comes the simulation. There is a quiz session also, so that you can test yourself while going through the quiz. There is some assignment, and in the reference section you will find the books from which you can go for further reading. There are also video lectures, okay, that are available on NPTEL. So this is a very comprehensive manner in which you can definitely get a clear, crisp understanding of a concept. So we will be directly going to the simulation part where we will be working on a forward biased silicon diode. Okay, there is definitely one test also where we can develop our circuit. I am not going to work with this, but this is kept as an exercise for you. You kindly try to do that. You can simply choose a diode. This 1N4007 you can find, and we can connect you can see this is the positive terminal of the battery. I will be connecting it to the anode of the diode since this is a forward bias condition. Before that I am to take the ammeters. Okay, so you can see the ammeter is through the circuit. You can take the voltmeter across the diode. You can connect the diode cathode to the negative terminal of the battery, and finally you can connect the ground. So this is how you can also connect the things, okay, in order to ensure that whether the circuit that you are developing it's correct or not. Then you can have this check connection. You can find there is some problem. You can go for uh, rechecking the same. However, we remember that the circuit that we had developed, it had actually no problem. Only the point is that this ground point has to be connected either here from there. Their program is such that only on this side that will accept the circuit. So the circuit was correct, but accordingly you can just go for them. That's why I am not demonstrating to this, because my concept of circuit might be different from them and the software might create some problem. Okay. So we will be going for forward biased condition of the silicon diode. So this is forward biased silicon diode. We will click onto that. You can see simply the circuit is ready in front of you. Alright. So what you need to do? You need to select the diode. Here also the instruction set is given. So there is absolutely no problem. You can take one step here, go back to the instruction and do accordingly. Okay, so first let us choose a diode. We will be choosing 1N4007, and then we will put a value of series resistance. I will put a value of series resistance to be 570 ohm. Alright, this is somewhere near 560. Okay, 560 ohm I have kept, because you can see the resistance is given in ohms. Now we have to set the DC voltage. So initially definitely there will be no voltage we will be applying in this power supply, that is the battery. This is how you can vary. You can see here you can vary the voltage. All right, so I will keep at the lowest value, and I will add this value to the table. You can find whenever I push this add to table button, then you can find the first serial number value is recorded in the experimental table. Then we will increase the voltage and we will this is a problem that you will face with this software. Many times they do not accept a small change in voltage. So I will go like this. You can see across the diode you have 0.548 volt, and this is the forward current. It has been recorded. I will increase a bit. I will add to the table. Now you can see when I am increased the DC voltage, that DC voltage is developed across this power supply, that is the battery. So what does that mean? We are actually applying 1.1 volt, but the voltage across the diode is 0.556 right now. And since the diode has not reached the cut-in voltage, you can find the current that is recorded is very less. Now here we can see it is 0.57. Here you can see the forward voltage is 0.6 volt, it is given. 579, 589, 594, and you can see here 0.596. Now you can find when we are very near to the cut-in voltage, the current increases. So now you can see that your recordings are being made, and in such a case you can go for this plot button. You plot it and you can find the characteristic of the diode in front of you. You can also go for this print option. If you print it, you will find a printout of this entire page. You can clear and you can go for maybe for a different value of resistance or a different diode. So in this way you can experiment, you can carry out the experiment while sitting back in your home, and you can just check out with the concepts that you have already developed while going through the theory course of diode. Now you see we will go for reverse bias measurements. Here you can find that the diode is connected in reverse bias configuration because positive terminal of the battery is connected to the cathode of the diode and negative terminal of the battery is connected to the anode of the diode. Again, there is a series resistance. There is an ammeter which is connected in series to the circuit, and there is a voltmeter which is connected in parallel to the diode or simply across the diode. So I will choose a diode that is 4007, and you can see we can apply up to 30 volt here. All right, and maybe we will be choosing a value of resistance. Here I will be choosing a higher value. I'll be going for 1000 ohm. Okay, then I will be varying the DC voltage. So initial value is 0.2 volt. I will add to the table, and then I will keep on varying the DC voltage. You can find I will be keep on varying the DC voltage. You can see that there is significant voltage in forward bias only in 0.6 volt. When it was very much near to 0.6 volt it started conducting, but here in reverse bias we have applied 14.8 volt. Still the diode is not conducting because you can find there is no current. You can see the current value is in microampere, so there is almost no current. Okay, so I will keep on increasing the voltage, and you may find that when it is nearing that 30 volt value, the reverse current has increased. That means the diode has faced the reverse breakdown conditions. So once it is done, we will be going for the plot, and you can find this is the voltage. Remember that this is reverse current. Okay, so it is shown in positive axis, but actually this is reverse current. You can find here this is reverse current. So sorry, but this is reverse current. You can find this is 0 and this is minus 30. So you should look like this axis. Normally if it is here, then it would have been very easy for you to just corroborate the thing, but here the axis, it is not put in on this side of the graph, it is put in this side of the graph. So you can find there is no current with the increase of voltage initially, and after that all of a sudden there is a very high increase in current. So this is the basic reverse bias characteristics of a PN junction diode, and I hope you have understood the concept, because there is nothing to understand the concept because already you have gone through the concept very clearly. and we have cleared every doubt in our theory session. But using this simulator, there is every possibility that you can simply clear your doubts. Now I would like to tell you that you can go for several experiments of your syllabus, like VI characteristics of a diode. You can go for half wave rectification, you can go for full wave rectification, you can go for Zener diode voltage regulator, BJT common emitter characteristics, BJT CE amplifier. You can go for resistance, capacitance, inductance. So this everything is there for you. You kindly use this facility. This is absolutely free, and I hope you will enjoy the sessions with virtual laboratory. Thank you for now. We will come out with another session with physical performance of the experiment. Thank you till then. And for any of your comments, please write in your comment box. For any confusions also, please write in your comment box so that we can get your comments confusions cleared. Thank you. Dear participants, in this session, we will be performing the actual experiment to study characteristics of PN junction diode. In order to do the same, we have prepared a very simple circuit. It can be seen here. The diode has been connected. It is seen, this is the diode. This is the anode of the diode, and on this band side, that is the cathode. The cathode is connected to ground, that is the common ground through the circuit. You can see we have taken out two terminals to measure the voltage that is developed across diode. So this is connected to anode of the diode, the red terminal, and this black wire is connected to the cathode of the diode. So this circuit is very generic. Here you can find this is the series resistance that we have kept. The series resistance can be directly connected to the supply through these wires. Actually, we have connected jumper wires like this. And when performing for reverse bias operation, we can simply desolder the diode and change its orientation. And these two wires you can find, if we short these wires, then current will pass through it. However, since we have to connect the ammeter in order to measure the diode current or the circuit current, we will use these wires to connect to the ammeter. So here is the board, and you can now see this is the power supply. This is a DC power supply, and it's a 3-channel power supply. You can find this channel, it can provide from 0 to 32 volt to a maximum limit of 2 ampere. The center channel, it can provide a constant 5 volt within a range of 0 to 2 ampere of current. And this channel, again, it can provide you 0 to 32 volt with 0 to 2 ampere current providing capacity. Now you see that this center channel, you can find the center channel is fixed. It will give you fixed 5 volt, whereas in this case you can vary the voltage that you can apply. Okay, you can provide up to 32 volt. Now you see this is the current limit knob. So if you want to limit the current in the circuit, you can use this knob. Okay, so here we will be using the power supply in constant voltage mode, and therefore we will be providing some current. We do not need a very high current for the circuit because we have used a heavy current limiting resistor. So therefore current will not flow to a very heavy amount in the circuit. However, if during such experiment, if you find that in this case you can find this current indicator, constant current indicator, it is at red. Okay, because the current button is at 0, it cannot provide any current. If you have to increase it, once you increase, this red signal is no more, the diode is off right now. Here you remember that if you come across such indication in your circuit, be very alert. It may so happen that there is a short circuit in your circuit, right? There is a short circuit in the circuit that you have prepared. Because under such circumstances, if there is a short in the circuit, then the current demand of the circuit increases drastically and the power supply asks for more current. Many times it happens that we do not understand the necessity and immediately we increase the current button. Okay, we increase the current supply. It may so happen in such a case that your entire circuit will be burnt and you may harm yourself also. So therefore, whenever this is red, be very careful to what action you are actually taking. Okay. So now you see, I will be providing some current and I will put the meters here. Before we start the actual experiment, we will perform an initial test in which we will try to see whether the diode that we are using is healthy or not, whether it is a damaged diode or it is a proper diode, it's healthy, that we will have to see. Now you see here, for that purpose we will make an initial measurement. This is nowhere related to the experiment. Okay, this red wire is connected to the anode of the diode and the black wire is connected to the cathode of the diode. We will use this meter and we will keep it in the range of 20 kilo ohm. Okay, you can see it is 20 kilo ohm and we will measure the forward resistance of the diode. That we will measure the resistance of the diode when it is in forward bias. Let us do that. We have connected it here. We have connected it here. And you can very easily see that, okay, I will be increasing. So you can see in forward bias, there is 26.5 K, this much resistance. Okay, there is no particular value, all right, but there is a finite value of resistance that you can measure. Now I will simply go for reverse measurement. Now I will be connecting the resistance of the diode in reverse bias condition. Now you can see it is over limit. I will be going for 2 mega ohm and still it is over limit. What does that mean? That means that in forward bias the diode resistance is less and in reverse bias the diode resistance is more. This particularly tells us that yes, the diode is healthy. Okay, because in forward bias, since the resistance is less, it will be very easy for us to make the diode conduct in that direction. So that's why it is very clear that the diode is completely healthy. Alright, now we will build the circuit. We have already told you about the circuit. So we have already built it. There is nothing very serious in this. Resistance is there. One side of the resistance is connected to the power supply. Other side of the resistance is connected to the positive of the ammeter. From the negative terminal of the ammeter, we are feeding the diode, anode in this case, and if it is in reverse bias, we will be feeding the cathode of the diode. And then cathode of the diode in this case is connected to the common ground. The ground is connected on one side to the power supply, and on the other side we are trying to measure the voltage across the diode. So anode is connected to the voltmeter positive terminal and voltmeter negative terminal is connected to the circuit common ground. So this is all about the connection. We will make it. You can see here this positive terminal. Okay, is connected to the positive terminal of the power supply. Alright. The common ground of the circuit is being connected to the negative terminal, and that's it. That's all from the power supply side. Now we are feeding power to the diode, but this supply can not reach the diode unless we connect the ammeter. Now you see here, when you are connecting the ammeter, be very sure about the polarity. So this is coming from the positive side, that's why it is red, and you connect it to the positive terminal of your multimeter. Okay, you do not commit a mistake here. So for a digital ammeter there is no problem, you will be finding a minus mark, but for a unipole single polar analog multimeter, it may damage the multimeter. Okay, so connect it to the common terminal. All right, and now you want to measure the voltage across the diode. Okay, so for that you take this anode to the voltage terminal. I will put it in volts, 20 volt range, and the circuit common is connected to the common terminal. So that's all with the circuit. I will be putting the current in the range of 20 milliampere, and here I will not keep on reading each and every value. I will wait for a while. If you are very interested, then you can note the readings so that you can plot a graph. I will not do that here. So I will increase the voltage. You have to look at this voltage. This I will increase, and you have to look at the voltage that is developed across the diode. Okay, so you see here, very slowly I have made it. Okay, I will go in steps of 0.1 volt. So you can see here we are applying 0.1 volt across the diode, and here also we can find 0.15. You can make it like this in order to get single digit value. This is just using the range of the multimeter. So that is 0.15 volt has been developed across the diode, and you can find in microampere range also we are having no current. Okay, now we will increase the voltage across the diode. So now you can see it is 0.25 volt across the diode. We have applied 0.2 volt. So same voltage we are getting in the power supply and in the diode, and we can find very easily there is no current. I will again increase the voltage slowly. So here now you can find 0.3 volt across the diode, and still there is no current. Now I will be making it 0.4 volt. It's 0.4 volt across the diode, and you can find there is some fluctuation that has started in the current meter. So now you can see we are actually narrowing the potential, that depletion layer. Okay, so now 0.5 volt across the diode. You can see the current has start increasing very slowly, but it is in the range of 0.14 or 15 milliampere. Now let us go for almost 0.6 volt across the diode. Okay, you can find the current has increased now to a good extent. Now you can see one thing, that although I am increasing the potential here, the voltage across the diode is almost fixed at 0.63 volt, and now the current has started increasing. Now if I keep on increasing the voltage from the power supply, you can very easily see that the voltage across the diode is remaining constant, whereas current through the diode is increasing, and it is increasing almost proportionally to the voltage. As we increase the voltage, the current is increased, but voltage across the diode is increasing very slowly, or almost we can say there is no increase in voltage across the diode. So we can say that the diode has reached its conduction state. The cut in voltage we have found, and you can see here 0.7 volt. At 0.7 volt there is almost no increase in voltage anymore. Whenever we are increasing the voltage that is being applied to the diode, the current is increasing. Okay, so the forward bias behavior of PN junction can be very easily verified in this manner. Now you see, we have to go for the reverse bias measurements. So for that, what we will do, we will simply disconnect the power supply and we will reverse the connection for the diode. So I am using a soldering gun simply to reverse the connection of the diode. I will remove the diode and I will connect the diode in reverse bias. Okay, let me connect, I will show you. All right. Now you can easily see that the terminal of the diode has been simply changed. You can see the anode here. Okay, you can see the anode here that is connected to the common terminal of the circuit, and this cathode terminal is now connected to the negative terminal of the ammeter. So now we can say that the diode is reverse biased. Alright, we have to absolutely make no further changes in the circuit. They can be all alike, and now we can connect the diode to the power supply. Maybe we will like to change the current range to microampere to see what is the minority current in reverse bias. You can see here now whatever current is there, it is in microampere. Okay, so now as I increase voltage across the diode, you can see here I am applying the voltage, the same voltage is reflected here and current increases. But remember, here the current is not being reflected in milliampere, it is in 0.4 microampere, so it's a very negligible current. You can see here as I increase the potential across the diode also increases simply in inclination to the voltage that is being applied. Now I will keep it in milliampere. When I take the meter in the milliampere range, that is the range that we had used for our forward measurements, you can find there is no current. Okay, so I will increase the voltage. You can see I have taken it up to 16 volt right now. 16 volt is being applied across the diode and you find no current in milliampere range, but in microampere you can find it is 15 microampere. It is 15 microampere. That means yes, your minority charge carriers are responsible for this feeble amount of current that is passing through the diode. I will go up to 20 volt and you can see that even now there is no current that is flowing through the diode, which shows us very clearly that in reverse biased condition, the diode does not conduct. The voltage across it increases, but it is not conducting. It will conduct only when the breakdown region is reached, the breakdown voltage is
reached. Okay, we are not taking our diode to the breakdown voltage, and that's all about the p-n junction diode characteristics. I hope you are very happy to see whatever you have studied in your theory course that is actually happening here in the lab, and whatever confusions you come across, you kindly mention it in the comment box so that we can get to you with the solutions. Thank you.